Hello, welcome back. So far, we have finished making all the elements. In this episode, we mainly work on the rendering and the materials. Concerning the fluid rendering, we mainly test the value of p-scale, the parameters involved in volume conversion, the voxel size, and some parameters on materials. Okay, let's start off with the main splashes. We render one frame first. This is how it looks. Good overall, but there is still room for improvement. First, the background mist is so thick that it covers some details of the whitewater. So I'll thin it a bit. Second, the foreground whitewater can be thicker. Currently, it looks kind of gaseous. The mist in the background. Let me bring down this P scale a bit. Then the whitewater in the foreground. Increase its density a bit. Concerning the whitewater in this place, I like to thicken it. Otherwise, due to low density, it will lose some details when surrounded by the mist. I'd like to increase the P-scale of the foam only and check velocity blur in these nodes. Okay, render it. It's done now. Compared with the previous rendering, the whitewater here looks much better. And there are more details now. I like it. The foreground whitewater is also better. After checking velocity blur, I think it's a bit overblurred. The shutter here controls its intensity, so reduce it. You may find there is some green at the edge. In fact, it's just a display error. This is the actual alpha channel. Check display options and toggle the transparency. Now the image is displayed with the correct alpha channel, the same as this one. Okay, let's go on. This is the rendering of the splashes on the right side. It's good overall, though there are a couple of small issues, just like the strange foams here. I think it's this pop simulation that goes wrong. You see, these points are still emitting particles. We delete them through H. And keyframe this parameter to avoid the other particles being removed. Just delete these particles when they are about to drop down. OK. The midground mist needs to be thickened a bit. My thought is to bring up its p-scale value. Besides, we can increase the overall stimulus. Select these VDBs and reduce the voxel size. Let's render it again. Alright. Compared with the former rendering, its level of detail is much higher now. When testing the rendering, we just tweak the splashes one by one, which can make things easier to handle. I rendered a few more frames to check if the fluid stays good all along. My attention is on the upper part, cause the small issues in the lower part are unnoticeable. So far, so good. Let's move on. This is the rendering of the fluid simulations at the intersection of the buildings with the tsunami and the mist above the ocean surface. We can see in some places the shadow is kind of dark, which means the white water there is a bit too thick. Let's see the white water in these two places. It's low in density and details. As for the shadow, we lower the p-scale to bring down the density, which can also improve the level of detail. Then check the rendering one by one and lower the p-scale where it's necessary. After that, increase the stimulus. To avoid the white water getting thinner, we duplicate a material and up its density scale. Reduce the shadow density a bit. As most of the splashes sit on the surface, too dark shadow is not reasonable. Let's change the material and render it again. Good. As to the mist on the ocean surface, it is a bit too thin. We increase its density scale. Reduce the shadow density somewhat. Then render it again. OK, done. Let's make a comparison with the previous rendering. This is how it looked before, and this is the current look. Zoom in a bit. This place was thicker before. And these places. After reducing the p-scale and increasing the density scale, the overall thickness of the splashes looks more reasonable now. As to the issue that the white water was not solid enough, it is fixed and with richer details now. Let's deal with another issue. Due to inaccurate calculation in the simulation, some particles get into the tsunami in collision. Let's move them up slightly. Good. We place a transform node after these simulations. Duplicate one and put it after the mist as well. Well, the p-scale of the background splashes in these two places is too large, and there's obvious graininess. causing a look of low details. So we reduce the P scale of the white water here. Reduce that of the mist as well. Let's come to the foreground white water. Reduce the P scale too. If we find it's too thin after rendering, we can increase its density then. Let's check the mist on the ocean surface. Let's say here. It's a bit more obvious than before, but too bright. I find the current smoke color is too high. Let's dim it down a bit. Okay, render one frame. The modified rendering, the previous one. The lightness is better now. As to the splashes in the two places, they miss some thickness when the P scale is brought down. But fortunately, there appear more details. Okay, let's simply thicken them a bit. Then render it again. Perfect. So much for the adjustment of the splashes. For a solid understanding of the rules of adjustment, I'm going to explain them in detail so that you won't feel confused when facing your own project. Here I made two conversions as the examples. The first one is like this. Though there are no obvious problems, the level of details is low. In fact, there are many details when we see the fluid particles. Let's see the edge of this particle clump and the variation in shape and density. After conversion, the shape loses some variation. So does the density here. In fact, it's not a matter of the voxel size. The edge could only become more rigid if we reduce that parameter, and the hole will look a bit thicker, but it's still of low resolution. Say we'd like to convert these particles to volume. If the converted shape is like this, it's absolutely low in resolution. But if this is your goal, it will end up with a satisfying rendering. This is another conversion based on the same voxel size. It captures more details. So P scale is the key factor in this background. If the quantity of particles is sufficient, I prefer to set a proper P scale in volume conversion. Based on that, if the volume ends up too thin, my first priority is to bring up the density. But if it's too thick, I'll reduce P scale. If the edge of volume is too blurred, then I'll choose to lower down the voxel size. As for the mist, if it's thin, I'll increase density. If it's too thick, reduce density. If the case is that the quantity of particles is insufficient, we can let more particles be emitted or apply a point replicate node. Sometimes I choose to up P scale and the voxel size, in the meanwhile bring down density. This way, the mist may end up with a better diffuse look. Note this rule is limited to mist only. Besides, we must know that the larger the P scale value is, the more RAM will be used. All in all, remember one point. The converted volume should capture the details of the particle clumps as much as possible. Based on that, we can make some adjustments as per our needs. Alright, in terms of the set of splashes, the same materials are applied and the operation is similar. And we will tweak the voxel size according to their distances from the camera. Okay, before merging all the fluids, we need to do some optimization. Otherwise, with a too heavy calculation, our PC may run out of memory. We ever deleted the particles beyond the camera view, and we can also delete particles behind the buildings. Import the buildings on the left. As the polygon count of the rendered models is large, which will definitely delete the solution, I convert them to VDB and then to polygon soup. This way we get a low poly model. Before deleting the particles behind the buildings, how can we determine if they are visible in the camera? We make it this way. First, let every particle send a ray toward the camera. If the ray can cross the position of the camera, it means the particle is visible in the camera. Likewise, if a particle is behind a building, its ray won't reach the camera. We subtract the position of each particle from that of the camera. Then we can get its redirection toward the camera and the distance between them. We assign the result to direction. Then, using the intersect function, let every particle send a ray toward the camera. If the PR returns -1, it means the particle is in our sight. If not, the particle is behind the building. Based on that, let's set an if statement. If the result doesn't equal to -1, then we judge this particle is behind the building and let it enter into the del group, the same group as the one here. Okay, there we go. The quantity is very large before optimization, and now it's much smaller. This way we can achieve the volume conversion in a faster speed, and the required memory will be reduced. As to other simulations on the left, I also optimized the way the particles beyond the camera view and the ones behind the buildings. Then I optimized these simulations too. Besides, I compressed the volume before caching. This operation is also good for optimization. I added volume compress nodes and file cache nodes for other splashes. However, there's no need to cache all frames out in the test. Just cache the frame that we're going to render. When rendering the splashes in the test, I usually set the scene as a matte object. The larger polygon count of the scene is, the higher RAM the rendering will occupy. So I set a time period when the dynamic buildings are enabled and clean up the unused attributes and groups on the buildings. Okay, I set up another building in the same way. Here I delete the simple buildings. Import the small stuff. Next, I'm gonna merge all the objects in the scene. There are cars, the small stuff, the ground, the dynamic buildings on the right and those in the background, and the buildings on the left. All are operable now. Drop a normal node to compute the normals. Well, let's first check the fluid part in the scene. I didn't render the tsunami for now. I love to reduce the gamma so that the atmosphere may look better. It's good on the whole. My computer has 64 GB of RAM. Actually, I failed to render all the elements out before optimizing the scene. The optimization saved a lot of my computer RAM. If hitting render to disk, you can see the calculation data report and the process of reading cache. When that's done, you can open the cache manager to clean up some unused caches. Hit clear all for several times, and the occupied memory will be freed up a bit. As we need to keep the project running during the rendering, more and more RAM will be occupied. which may cause our computer to run out of memory. If selecting Render to Disk in background, we can quit the project to save some RAM. Okay, let's move on to materials. We start off with the small stuff. These groups help a lot when we apply materials to objects. There are so many shaders in this scene, so I'd like to use my own tool. You know, the default UI of the material is arrayed horizontally. If there are too many textures, it will be inconvenient to check them one by one. Plus, for me, there are many useless functions. It's good enough to assign a shader as per the corresponding group. Here are the shaders of all the stuff. We just need to apply them correctly to different groups. Alright, I'm done with that. I added some trees along the roadside and in the middle of the road. Here is the process of tree arrangement. Very simple. Here is the shader setting. As for other objects, I also apply the shaders. You see the textures can be displayed normally, which proves the shaders work well. The view is a bit frozen when displaying lots of textures, so toggle it off. So far, I'm done with all the shaders. Because the more shaders Houdini loads, the more RAM will be required during rendering. We can make some further optimization to reduce the memory footprint. I classified all the objects by whether it's dynamic or not. The left are static, like the cars, the traffic facilities, the ground, and the buildings in the background. The rest are dynamic models, like the cars, the small stuff, and the destroyed buildings. For the static objects, I'm gonna cache one frame out, copy the path of the cache, jump into the material network, drop a delayed load procedural node, and paste that path. To avoid confusion, this shader can be set the same name as the cache. Drop a geo. Under Geometry of the Render tab, select the shader we just created for Procedural Shader. Uncheck this checkbox. Keep this geo empty. When we render it in Mantra, those static objects will be rendered out. Actually, this material allows the renderer to read the static models from cache. Thus, this approach can speed up the rendering and save some RAM. Of course, you can handle dynamic objects in this way, but with too many dynamic objects in the scene, a cache file per frame takes a few gigabytes. If caching all, we need a large disk space. So I prefer not to do that. I apply the same way to the splashes. Okay. After setting the paths of the materials, we apply these shaders to the corresponding simulations. When we're done with that, the nodes inside it will be invalid. But that's okay, just let them be. Let's move on to other simulations. Make sure the paths are set correctly. Okay, done. Let's render it. Here are all the models, splashes, and the mist. So far, so good. This is another rendering. There are only the static objects without any materials. That's because I forgot to select Save All Materials and Shaders. After selecting it, the models can access their corresponding shaders. Okay, cool. I didn't render the tsunami together. I'm afraid of my computer running out of memory, so I'll use another mantra to render the tsunami individually. Later, we just need to put the tsunami rendering at the bottom in compositing. Because there's no fluid under the tsunami, naturally the intersection won't exist. Regarding the tsunami render layer, there are no textures, so return it to the default. The final frame range is 1 to 150. Tick Allow Motion Blur and check Shading Normal. We still need the Z depth channel in the UV channel. By default, their output is of low quality with obvious aliases at the edge. So I'm going to show you how to output high quality depth and normal channels and drop a global node. Multiply is PZ by out of. If there exists a transparent or translucent object, then we need to do this operation. This way the depth channel will be correct. Then the position channel. First, transform the space. Keep the default space here. Also multiply it by out of. Then the UV channel. We need to unwrap the UV of the tsunami mesh. Now the tsunami gains the UV attribute. Usually I'll set and output these channels in case you require one of them in compositing but you don't have it. It'll definitely waste time to render it again. Get into Mantra. Let's set the channels. Select the float type for Z depth. OK. Increase the pixel samples and keep the diffuse SSS and volume quality off. There only exists reflection and refraction in this mantra. Reduce the reflect limit and the refract limit. You may need some tests for proper values. To get an efficient rendering, we can optimize it as much as possible. Reduce Z importance under dicing. It can optimize rendering through reducing details based on depth. Let's take the tsunami for example. It controls the detail attenuation of the ocean displacement from near to far. The smaller it is, the more details it will lose, yet the faster the rendering is. It's okay to reduce it a bit, as long as the rendering image ends up well. Okay, let's set the objects to be rendered. Render ocean. Render ocean mask is the object that covers the bottom of the tsunami, then the tsunami volume, and those low poly buildings. Come up here, let's set the render resolution. My final rendering image is 1920 by 1080. In the test period, I set the resolution to 1280 by 720. Okay, let's render it. Wonderful. Let's check the channels. So far, so good. The last ones are light channels. There only exist reflection and refraction in this mantra, so we only need to confirm these 4 layers end up well. Nothing wrong. Concerning the tsunami, there is some noise on the surface. So I'm going to up the sampling quality of the environment lights. Okay, done with this mantra. Let's get down to the scene and fluid. Check shading normal. Yeah, it's just for models. We still need to set channels for all the fluid. Unlock these shaders. Let's first set the normal channels. Add 3 constant nodes, which represent X, Y, and Z. Regarding the values, it's fine as long as they are larger than the scene. We transform the camera space to world space. Add 3 filter shadow nodes, which send rays along the X, Y, and Z directions. Then combine the 3 components together and multiply the result by out of. Now we have got a good normal channel. Then we set the Z depth and the position channels. We directly copy from previous settings and paste to other fluid shaders. Next, let's set up the mantra. For the all comp here, we select No Lights Exports. We have set the position channel for the splashes and mist, not for other models. If we set them one by one, it will take a very long time. There is another method. Add a constant shader and get into it. Set the position and Z depth channels. I will override all the models with this shader. There's no transparent or translucent object, so we don't multiply it with out of. Then drop a new geo. Import all the models. There are the trees, the static models, and the dynamic models. My computer will freeze to display them all, so I won't do that. Clean up all the groups and attributes. And add the shader we set just now. Duplicate another mantra. Only keep Z and P channels. And delete others. Check Allow Motion Blur. In this mantra, there's only a constant shader, so we can reduce some sampling and quality. Set the reflect limit and refract limit to 0. Reduce these parameters. The light render layers are not needed in this mantra. Get rid of these. OK. For the scene mantra, I forgot to add the crypto matte layers. Let's add it. Select the property to generate IDs from. You can choose material name or object name. We select the material name. Then the number of materials equals the number of IDs generated. Objects with the same material share the same ID data. Later, when we want to extract their masks, it will be very easy. Very convenient. Yet crypto matte will not be displayed in the render view. Only when the rendered image is saved into disk, the crypto matte layers can be stored, so we will check it in compositing. Check Allow Motion Blur. Reduce the max resamples a bit. This way the rendering can be faster. Well, the noise will increase subsequently. We can check the rendered layers here and find out in which layers the noise is too much. Then we increase the sampling accordingly. Besides, I'd like to up the diffuse quality a bit, so does the refraction quality. This way the sampling of the transparent objects such as glass can be improved. Return the volume quality to the default value, 1. As there are splashes and mist, volume shadow step rate can be lowered a bit. The lower it is, the more noise there is in the volume shadow. Yet the rendering can be sped up. Also, decrease the reflect and refract limit. No point to keep them so high. Dicing here. Reduce these parameters. Though we have optimized many render parameters, the rendering result is barely affected. Then we check if the rendering objects are set correctly or not. So much for these three Mantra renderers. Let's render it and see how it comes. OK, done. Compared with the previously rendered image, we can see the noise is much less than before. Mainly because we improved the sampling quality of environment lights, but a higher sampling indicates a longer rendering time. Let's check the render channels. This is the normal channel of the scene without splashes. The normal channel we set for volume, then Z depth of the splashes, and the position channel. Everything goes well. This is the position channel of the scene. And the Z depth channel. There are two only. Good. So everything goes well. We can render the sequence in the background to save some memory. So far, we're done with the work in Houdini. See you in compositing.